Swayam Prabha. Digital India. Educated India.
So, as we have seen in the last lecture that I have shown you how to derive the free energy of a regular solution, but mathematics will not say everything. Mathematical equations are always just to calculate different parameters and values. The graphical representation of these equations are actually more vital. That is why you come to know the science of solid solutions, how the solid solutions are stable, whether they are unstable or metastable, it will be all clear from these diagrams. So, let us move forward. I discussed with you the first case for the regular solutions, where for the value of omega less than or equal to 0, I have told you two separate cases. One case when temperature is small, other case when temperature is high. If temperature is small, obviously the entropy contribution is small, because entropy has minus T delta S mix, and delta S mix is nothing but R into minus R into log of A, XA into log of XA plus XP into log of XP. So, in other way, temperature increase will lead to increase of this term. Delta H mix will not change drastically, it will be having small changes. So, if the entropic term is increasing as because of increase of temperature, solid solutions will be more preferred, but more or less preferred has no meaning. It is basically solutions will be always preferred for any value of omega less than or equal to 0. So, now we are going to look at when omega is equal to more than 0. Okay, that means it has a positive value. So, if that is the case, then what is going to happen? So, we are again going to discuss two cases when temperature is high and temperature is small. Okay. So, if temperature is small, what will happen, and temperature is high, what is going to happen? So, simply I erase these color plots on, I make the same plots on these, so that you can follow it up more. Only thing we have to do is that we have to increase the y axis, because now because it is high, more than gamma is more than or equal to 0, more than 0 actually, or higher than 0. So, therefore, we need to plot it on the positive axis also. Okay. So, for t equal to small actually, as you see when t equal to t is small, the entropic contribution is small, correct, because t is present in this equations. Because it is present in the equation, therefore, value of entropic contribution or delta S mix will strongly depend on temperature, or T delta S mix will be higher, or so will be lower, not higher. So, let us first plot what will happen to delta H mix. Obviously, delta H mix, because omega positive, it will be positive. So, this is what is your delta H mix now. Entropic term will be always negative because of the nature of the logarithmic terms. Xa and Xp are fractions, so log of any fraction is always minus. So, but it will be low because temperature term is low, correct. So, what will happen then to delta G mix? Okay, what will happen to delta G mix? That is where the interesting situation comes, because delta G mix is summation of these two, one is positive, other is negative. As you see here, when xb, this is a function of xb, right, this is a function of xb, when xb is small or xb is very high, in these two zones, range of values xp small or range of value xp high, in these two zones the value of H mix and delta what is called delta T delta S mix is almost similar. So that means that this value, in fact delta this value will be little bit higher, so therefore negative contribution is more, so this will go up, so go down and up, and it will be like this. So that is my delta G mix. Okay, so that is what is going to happen. So that means what? Delta G mix passes through it starts with 0, goes down, then again it increases, reaches a maximum value and decreases, and then again becomes 0 at xb equal to 1. So that means delta G mix has an inflection point, because it was a downward slope and there is an upward slope, and when these two slopes will match a certain point, it will have an inflection point here, inflection point there. Please remember this plot, because this plot is very important for many phase transformations. This one will help us in understanding many phase transformations. Okay, now let me move a little further and explain what will happen when sigma more than equal to 0 but temperature is high. What you can see here, when temperature is high, as I said in the last lecture also, the important aspects of important contribution because of temperature high is coming from the entropic term, because T is directly visible here. So therefore entropic contribution will increase substantially, but enthalpic contribution which is coming from the sigma xxp will not change much, because we know that bond energies do change as a function of temperature, but normally they do not change drastically. So therefore delta H mix will remain almost similar, it may change little bit. Okay, so that is my delta H mix. Okay, so I write it delta H mix, and entropic term as I said will increase because of temperature, so this will go down much further. And because of that the enthalpy, because of the free energy will also be, free energy will not be like this, it will be somewhere lying like this, because this is summation of these two. But whatever may be the situation, oops, I am sorry, I should draw it the real red chalk. Okay, so that means what? Again, even if you have positive value of sigma, omega leading to positive value of a delta H mix, because the contribution of entropic term is so high at high temperature, delta G will be again negative, and look, it is a parabola, inverted parabola again. So what we found, that for the three cases, when sigma, if gamma is more than 0, temperature is high, when gamma is less than 0 but temperature is low and high, solution is preferred. This is very important in metallurgy and material science, because thermodynamics tells you what are the possibilities exist, okay, and rather it is more logical to say it talks about impossibilities. So thermodynamics tells you that under these three conditions solutions will be easily formed or preferred. So because of that, alloying is so versatile, alloying can be done very easily. That is the reason, because thermodynamics promotes alloying, thermodynamics helps us to form alloys, it tells you that it is possible to form alloys. That is the first conclusion which you can draw from these plots. Even using simple regular solution theory I can tell that. If I move on further I can even conclude most important things. Second important aspect, it tells you that it is rather impossible, I would say impossible, to prepare a 100% pure metal because of increase of free energies. See, as you see, if I make a metal more and more pure, suppose if I try to reduce the solute, if I try to reduce the Xp concentration, this is Xp. So if Xp is 1 here, Xp is 0 here. So, by making pure A, I am reducing the XP concentrations. So, by making XP concentration as small as possible or rather vanishingly small, what I am doing? I am making delta G mix very low, or I am actually making delta G of the solutions or G of the things higher. So, that means that this higher G phases which having higher G is not stable, which we know that from the our discussion that G relative values of G of different phases tells you whether they are stable or not stable. So, that is why it is impossible to make 100% pure metal except few, maybe gold or silver. It is very pertinent that thermodynamics makes you tells you a upper bound of purity. You can get maximum 59 or 99.999 or 99.999 or 69 purity, but you can never achieve a purity of 100% because thermodynamics will be violated then. This is the main reason of not having purity. So, alloying is, in a nutshell, alloying is more easily possible in systems like metals or ceramics, because alloying will reduce the free energy of the system, and by reducing the free energy of systems we can simply make the solutions formed easily. And this has changed the civilization, because without alloys civilization would not have seen the application of materials which we now see like steels or aluminum alloys or titanium alloys, copper alloys is only possible because of alloying. So, a whole theory of alloying is based on these quasi chemical, or I would say not fully based on, but I would say that primarily based on these concepts of these thermodynamic concept of solutions and the quasi chemical theory. So, that means in a very simple fashion I would say that it is possible actually to explain all the phase transformations behavior even using these 4 different plots, which we will see later. So, in the next 5-6 minutes or maybe 7-8 minutes whatever we have, we are going to discuss with you some other things like more about chemical potentials. So, as you know that chemical potentials actually tells you in a alloy or in a solution the stability conditions, and I told you the stability conditions in the last class. The stability conditions tells you the chemical potential of a phase of a component in both the phases must be equal. So, that means what? Graphically we have seen how to determine chemical potential in the last lecture, even last to last lecture also, but mathematically we should also know how to calculate chemical potential. So, chemical potential, as I told you, comes basically because of the free energies, it depends on the compositions, and we know that chemical potential is given by this function. At a constant temperature pressure is nothing but derivative taken for G as a derivative as a function of Na, or Na is the number of moles of A, and this can be again converted to the mole fractions. And I told you in the beginning in the last class that G as a constant temperature and pressure is nothing but mu A XA plus mu B XP, correct. So, what is the actual expression of mu A? Mu A is related to GA0 plus RT log of A, remember that, where A is activity of A in solution, it may be liquid or solid. Similarly, and GA0 is the free energy of pure component, T is the temperature. Similarly, mu B can be written like this. Now, I will not do the detailed calculation, this will be part of your question or assignments whatever we will be providing to you. You need to do the homework, and you will find that this mu A can be written in terms of mole fraction, because see ultimately activity is what? Activity is tells you whether what is the propensity of a component to form the solutions, or propensity of a component to react. That is what is activity. We know that for calculate activities, you know from thermodynamics that we need to demarcate between solid, liquid and gas, but it is always better to convert activity in terms of mole fractions. And we know for the Raoult's law tells you that in a liquid solutions activity is equal to mole fractions when it is dilute or very concentrated. Okay, that is A reagent and B reagent I can always apply Raoult's law, but only when you prepare solutions or liquid solutions which are having concentration in the middle of the XB or XA values like 0.4, 0.5, 0.6, 0.7 or even 0.8 or 0.3 of XB, the deviations from the Raoult's law is observed. So that is why you need to know what is the actual expression of the chemical potentials as a function of mole fractions, and it seems these are related to the gamma. Okay. So this is GA0 plus gamma multiplied by 1 minus XA square. This is what I am asking you to derive, XA square plus RT log of XA. So what I convert? I convert from here to this. What I added is two terms, basically one term, sigma, this is multiplied by 1 minus XA square. Okay, gamma multiplied by 1 minus XA square plus RT ln XA. Similarly, I can write down the chemical potential of B is equal to GA GB0 plus gamma 1 minus XB whole square, okay, plus RT log of XB. It is very easy. This actually comes down directly from the expression of G I have given. So G is basically equal to GA0 plus sigma XA minus XP plus the entropy terms. From there it comes, okay. But you must know that relationship between this and how it is related to a function of G mix regular, that you should derive yourself, and then you can get down these two equations, both chemical potential of A, chemical potential of B as a function of XA and XP. This is important because you will like to plot these chemical potentials at a fixed temperature for different values of mole fractions of A or B. And then because the chemical potential actually determines this relative stability of the phases. Stability of the phases depends on the equal chemical potentials are equal or not at the interface or it is not true. So finally it boils down that this whole theory of quasi-chemical theory allows you to not only get the G or delta G mix of regular solutions, but also calculate the chemical potentials. And by plotting, in the next class I am going to discuss that by plotting the chemical potentials as well as the delta G mix as a function of XP at different temperatures, we will be able to tell whether a particular phase is stable under a temperature at a particular temperature or not very easily. So before I wind up this today's lecture, I would like to tell you that thermodynamics form the basis of both phase diagrams and phase transformations. In fact, we are going to further discuss about the effect of what kind of solutions are there, whether it is order or disorder. If it is order, what will happen to the free energy expression? Because this here we are not talking about any ordering or clustering, we are simply considering it is a random solution. That means atoms of A and B are randomly arranged inside the solutions. They are not sitting, they have no sitting preferences like many students have, right. So they can sit anywhere in the lattice A and B atoms, and that is a random solutions, but that may not be true always. So in many cases we will find order solutions, many cases we will find partially order solutions. What will happen to the free energy when this situation arises? Again you have to modify that regular solutions the free energy expression from the available from the regular solution model. We will modify it and we will plot it and show you what will happen in the next lectures.